In this lecture, we are going to begin going over the minimum spanning tree. And before we start talking about a minimum spanning tree, we just need to get an understanding of what a spanning tree is and what the rules are for it. So we have three rules. The first one is we need to be connected. The second one is no cycles. And the third one is the number of edges is equal to vertices minus 1. So number of vertices minus 1. So we'll start with something simple, and we'll say that we have 0, 1, 2, and 3. And we're going from 0 to 1, 1 to 2, 2 to 3, 0 to 3, and 3 to 1. So we see that we're definitely connected. We're able to get to every node from any node through some form of a path or another. But we see that rule number 2 is currently being broken here. So this is currently not a spanning tree, because we see that 0, 3, 1 is cyclic. We can go 0, 1, 3 cyclic, and I mean we can make a couple of cycles out of this. But we also see that we have more edges than we do nodes. So too many edges in this case as well. So for us to make this a spanning tree, we can do 0 to 3 to 2 to 1. That's a spanning tree. We can do 0 to 1 to 2 to 3. That is a spanning tree. And we can also do 0 to 3 to 1 to 2. And that is also a spanning tree. And we can continue making more spanning trees out of this, but I just wanted to show you some examples of what a spanning tree looks like. So these are all spanning trees. So if we want to start looking at a minimum spanning tree, then the sum of weights, the sum of the edges, weights should be minimum. Alright, so if we take our same example from above of 0, 1, 2, and 3, and now we start assigning some weights to them. So we have 0 to 3 is 2, 3 to 2 is 1, 0 to 2 is 3, 1 to 2 is 4, and 0 to 1 is 5. So if we want to create a minimum spanning tree to this, then we want to satisfy our three rules above of it being connected with no cycles, and the number of edges is equal to the number of vertices minus 1. So for us to do this, we can start out at vertex 0, and we see that from vertex 0 we can go to 3 or to 1, but we see that we have an edge of weight 2. So let's take that. And then from 3 we only have one path that we can go, which is 1, so we can go to number 2, vertex 2, and we see that we can go from 2 to 0 or 2 to 1. But if we take 2 to 0, then we create a cycle. Therefore, there would no longer be a spanning tree. So our only path that we can take here is going to be to 1 as well. And now we have a connected graph, and we are minimum because we have 2 plus 4 plus 1 is equal to 7. And every other path that we take from here to create a minimum spanning tree will be greater than 7. So that was a pretty simple example that we could look at. And so now we can create a slightly more complex graph where we can say 0, 1, 2, 3, 4, and 5. And we can have 1, 2, 7, 2, 1, 3, 6, 4, and from 4 to 2 we will go 3, and from 1 to 3 we will go 5. So we'll start at vertex 0 again, and we see that we can go two different directions. We can go to either vertex 5 or 1, and we'll go with vertex 5 because it has a weight of 1. From 5 we can go to 4, or we can go to 1, and again we'll choose 4 because we have the lower weight on that edge. From 4 we can go to 3, or we can go to 2, and if we go to 3 we have 7 as our weight, and if we go to 2 we have 3 as our weight. So we'll go to 2 since we have a weight of 3. From 2 we can go to 1, or we can go to 3. So we will go to 1, and from 2 we can also go to 3 where we have a weight of 2. So here the weight of our minimum spanning tree is going to be equal to 9. And we see that we are connected entirely. We have no cycles, and we have 1, 2, 3, 4, 5 edges, and we have 1, 2, 3, 4, 5, 6 vertices. So this would be our minimum spanning tree. So in the next lecture we will go over the implementation for a minimum spanning tree. So if you have any questions about a minimum spanning tree, please feel free to ask me in the Q&A section.